Hi, I'm Dr. Viv, and I would like to talk about ways of multiplying vectors. Now, I just want to recall what you already know from before, and that is what you may have learned in earlier courses in either physics or other places you learned vectors such as calculus, multivariable calculus, and that is dot product and cross product. This is popularly called the dot product instead of a scalar product, and that is popularly called a cross product because that's how they look, like a dot and a cross respectively. So I'll first describe the two vector situation, and then for the purposes of this course we'll then go to three vectors soon. We'll find a way of doing scalar product for three vectors and vector product for three vectors. That will be the subject of the following two videos to this. What say this notation might initially strike you as being excessive, but mathematics always proceeds by refinement of notation. Now, if a mathematician looks at this, he immediately can tell you a couple things. He can say that, oh, to make a dot product, you got to take a vector from R3R, you got to take another vector from R3R, and somehow mingle them together by this procedure known as dot, and you'll end up with a real number. The output is a real number. The input is two vectors, output is a real number. This cross has nothing to do with the cross product. This is called the Cartesian product of two vector spaces. Now, cross product, if someone looks at this, they'll say, oh yeah, you take a vector from here, take a vector from there, you do something called the cross product, and then you'll end up with another vector. The output is another vector. So that's how these notations help you understand what's going on. So let's first define the dot product. That's not a definition, that merely tells you what the output looks like. When you actually have to define it, you have to tell people how the object is defined. So A dot B, if I take two vectors A and B, their dot product can be given in two ways: AX BX plus AY BY plus AZ BZ. Now what am I doing here? I'm just multiplying the x components together, the y components together, and the z components together. Could not be simpler. There's another way to do this, especially in polar coordinates. And if you're given the vector A in polar coordinates and the vector B in polar coordinates, you can certainly find the angle between A and B by subtracting the two angles. And that angle we'll call theta. Then you can find the length of the vector A separately and the length of the vector B separately using the Pythagorean theorem. So A is going to be the square root of AX squared plus AY squared plus AZ squared, and similarly for B. So that you can do off to the side. And then you can form the dot product the following way. That's a pretty nifty way of writing the dot product. So what I've done here in the background is I've written A first as A comma some alpha and B as B comma some beta, and this angle theta is just the difference between alpha and beta. I'll put the absolute value sign because it doesn't really matter if the difference is positive or negative, since cosine eats up the negative sign right away. So this is a definition of the dot product. Now, just for reference, the angle between A and B is taken to be the smaller of the two angles. There's another angle, which is this one, 360 minus that angle. We always take the one that is smaller than 180 degrees. If it's exactly 180 degrees, then you don't have to worry about it. But if it's less than 180, then you choose the one that is smaller than 180 to write this. What are some of the properties of the scalar product? First of all, what is a good geometric way of thinking about it? What is A dot B geometrically? Suppose I have a vector A in this direction and a vector B in this direction. What does A dot B really represent? So first of all, let me take the projection of A onto B. Well, that projection is going to be A cosine theta. So this projection vector is going to be A cosine theta times a unit vector in the direction of B. Let's call that unit vector B hat. So this is the projection of A along B, sometimes denoted like this in mathematics books, proj AB. Okay, that projection vector, what are we doing to it? We are multiplying A and A cosine theta times B with the B instead of B hat is essentially the projection of this entire thing. So this length is A dot B hat, and so A dot B is just the magnitude of the projection times the magnitude of the vector B. So it's just that. So if the magnitude of the projection is just A cosine beta, and so that's going to be AB cosine theta. So that's the geometric interpretation. It's just a projection of the vector A along, or you can also think of it as a projection of the vector B in the direction of A. I'll leave that as an exercise for you. Some basic properties of the dot product is that it's distributive. So if I have the sum of two vectors, so if I have B plus lambda times C, where lambda is some real number, then this is going to be A dot B plus lambda A dot C. So that's one way of writing the distributive property, and then you also have the property that A dot B is the same as B dot A. Finally, when is A dot B 0? From looking at this formula, we can see that A dot B is 0 if and only if, provided A and B are not themselves zero vectors, A dot B is 0 if and only if A is perpendicular to B. So it gives us an important criterion for when two vectors are perpendicular. That's a very useful fact about the dot product. Now, there's one more factor that we have to consider, and that is, what does the norm look like? The norm of A itself, if I think of the vector A by itself, the norm of A is, let's write down what it is. It's ax squared plus ay squared plus az squared. But that can be written as the square root of A dot A, because A dot A is A times cosine 0 degrees. So it's just A squared, and A squared is ax squared plus ay squared plus az squared. So this is sometimes called the norm induced by the inner product. It's very useful, especially when we go to function spaces later, to find the norm in any function space which is infinite dimensional vector space. Now let's talk about the cross product. The basic definition of the cross product comes from the matrix definition. A cross B is the determinant of the following matrix. For the first row of the matrix, you write I hat, J hat, and K hat, which are the three unit vectors along the I, J, and K direction. For the second row, you write the X, Y, and Z components of A. And for the third row, you write the X, Y, and Z components of B. This then completely specifies our cross product. Let's work it out by the usual rules of determinant. It's going to be I hat. Remember the assignment of signs. This gets a plus sign, that gets a minus sign, and that gets a plus sign. To familiarize yourself with determinants, go back and look at one of the earlier videos I had on finding the determinants of a 3 by 3 matrix. and you'll see that I make these sign assignments there. So now let's go to the evaluation of it. It's I hat times AY BZ minus AZ BY. And then there's going to be minus J hat times AX BZ minus AZ BX. The last term is plus K hat times AX BY minus AY BX. And we have done it. We have found the components. That's Cartesian. Now if you had it in polar, how would you do it? That you had two definitions there too for Cartesian and polar. Let's try this in polar. If I had A cross B in polar, if I had A in polar and B in polar, how would I do A cross B? Well, first of all, I can find the angle between A and B by simple subtraction, and then A cross B will end up being AB sine theta times some other vector n hat. Well, that's the rub. You cannot really do better than that. Okay, I've given you the magnitude, it's AB sine theta, but the direction is n hat. How is this n hat defined? It involves a pretty hilarious procedure. You take the right hand fingers, and those are those four fingers, not your thumb, and curl them in the only possible way you can curl them without going into the ER, and that is in this direction. Curl from A to B, and the direction of the thumb gives you n hat. So this is not a very user-friendly procedure because you can't really do better than that. So n hat is a thumb direction, but it's perpendicular to the plane of A and B. So that's one thing you learn in this way of doing it. There it was not very transparent what A cross B is. It's some random vector with I, J, and K components. But here you learn something interesting about the cross product. The cross product is always going to be in a plane that's perpendicular to the plane of A, plane containing A and B. In other words, the cross product educates you if you're a two-dimensional creature like an ant scurrying about on the surface of a pie, for example, that's cooling in the windowsill. So if you're that ant and you're pretty intelligent about mathematics, then you could have deduced the existence of a cross product or a third dimension, not by looking up and seeing the sky, but rather by simply going in one direction towards the crust, another direction tangential to the crust, and taking the cross product, and you realize, wait a minute, the cross product is not anywhere on the surface of the apple pie. It's either inside the apple pie or it is outside the apple pie. And from that basic manipulation, you can figure out the existence of the third dimension. There is another way of writing this cross product in determinant form. Now, if you look at the determinant videos of last week, you will find that you can also write this in terms of the Levi-Civita tensor. So the ith component of the cross product is given by epsilon ijk aj bk, where Einstein summation has been used on the repeated indices j and k. So remember, I, j, and k can take values of 1, 2, and 3. So I have to also tell you that a1 is the same as ax, etc. a2 is the same as ay. So you have to do that. Now there's another subtle thing which I'm not going to dwell too much time on here, and that is, how do you really find this angle between two vectors? Okay, I want you to think a little bit about that. It's not easy to find this angle between two vectors. I said by simple subtraction initially, but I was really thinking of two-dimensional vectors then. But if you live in 3 dimensions, you have these direction cosines, as we saw in the previous video. It's not very easy to subtract direction cosines and come up with a single angle. So here's a hint of how to do it. One way to do it is to use the dot product. So what we can do is to find theta, we we can follow the following crazy procedure. We can write theta equals arc cosine of A dot B divided by A times B. Well, once you find theta like that, then you can find sine theta by putting it back here. So it's actually a fairly arcane way of doing the computation. So if you have two three-dimensional vectors, if you want to find just the magnitude of the cross product, A cross B, without too much sweat, then the procedure is, it is A times B times sine of arc cosine A dot B over AB, where A and B each are given by their respective three-dimensional Pythagorean theorems. So that's a fairly nifty looking formula there.